Now that we have understood why properly computing loads is important, let's focus on how to do it using SAMSEV4 wind turbines loads. Wind turbines are usually divided into several main components: the rotor, including the blades, the rotor shaft, the bed plate and the main frame, the gearbox and its housing, the high-speed shaft, including brake and slip clutch, the generator and its frame, and the tower. This division is reproduced in our SAMSEV4 wind turbines environment. Each component is a member of the data tree and is represented by a separate model. Component models can be selected independently. These models are then assembled in the turbine as a whole. Models for each component include parameters for every piece of data that can be modified during design. The model's accuracy varies from very simple to very detailed, depending on the goal of the computation. Component models have been regrouped into families to create global models easily. Even for the simplest models, all of the shafts, tower, and blades are modeled with beam elements made up of 6 degrees of freedom per node in order to properly represent shear, bending, and torsion phenomena. Since beams are used, the user only needs to define geometrical properties, like the radii of the tower, but not to compute equivalent masses and stiffnesses in addition. In simple models, gearboxes are usually represented by rotational speed ratio, as well as by mass and inertia properties of the gears and housing. Stiffness of the yokes can also be added. A generator, in the simple model, is represented by its inertia and mass properties. The corresponding torque versus rotational speed curve is usually an input driven by the controller of the turbine. As already mentioned, each component comes with a full set of parameters that describes it. We have here the example of the tower model used for simple computations. One can define its height and hollow conical profile. Its foundation can also be defined, or it can remain undefined in case the user wanted to add an extra component representing the ground, or some features specific to offshore turbines. But we'll come to that in the structural dynamics presentation. Once parameters have been changed to fit the model to the real component, this model can be stored in a library to be reused later. That way, users can easily build their own library of components and have access to them easily. This library can even be shared between the team members or with partners so that everyone uses the same pool of components and works in a coherent way. Collaborative work is a must today in our highly competitive environment, and SAMSEV4 wind turbines is the right tool to do it the right way. One of the main features that any software dedicated to wind turbines should have is a correct way to evaluate loads produced by wind on the blades. As we saw earlier, wind loads cannot be represented by equivalent forces computed beforehand. Effects like blade deformation or tower shadow have a major impact on the load distribution and cannot be computed properly without coupling between aeroelasticity and mechanics. Blades must be modeled by taking 2 distinct features into account. One relates to its mechanical properties, like its stiffness and mass, however these are input, and the other to its aerodynamic properties. Both are eventually linked by the fact that, firstly, the aerodynamic elements have the same topology as the mechanical ones, and, secondly, aerodynamic properties are to be defined at the same spots as mechanical ones. Transforming wind properties into mechanical loads is achieved using the blade elements momentum, or BEM, theory. Gusts and turbulent winds can be defined as load cases. Of course, the tower shadow effect is also taken into account, since it is responsible for most of the 1p frequency vibrations. As far as control is concerned, our approach is to fit as much as possible to the market standard. To do this, we can use external dynamic link library, or DLL files, compatible with the format used inside Bladed. If necessary, our controllers can act on yawing, brakes, and pitch for each blade individually if required. Parameters used by the controller can be stored in a file to prevent the user from having to rebuild the DLL file every time a parameter should be changed. Again, this parameter file is compatible with the format used in Flex5 or Bladed. We have seen in this part of the presentation that our software, SAMSEF4 Wind Turbines Loads, comes with pre-embedded models for each component of the wind turbine. So, these models are easy to customize thanks to full parameterization. SAMSEF4 Wind Turbines is able to represent more types of structural behaviors than most software packages on the market dedicated to load computations. For example, blade and shaft torsion can both be represented. In addition, the models are small enough to run in real time. Finally, the ability to store components in libraries and share them makes load computation more efficient and user-friendly.